Hello everyone. During this lecture, we are going to focus on lectures 22 and 23. The topic is biopolymers food industry applications. Biopolymers have been widely used in food industry. Okay, first, biopolymers are one of the major material for food packaging and coating. Before we talk about the polymer packaging coating, so let's talk about food preservation first. So there are different gases related to food preservation. Okay, we know oxygen in general it is not desired because oxygen accelerates oxidative reactions, which leads to off odor and off flavor. Okay. Besides that, there are also color changes, reduce the nutritional quality of the food. But sometimes for food, you do want oxygen. One good example is meat. So for meat, we know the color is contributed by the myoglobin, right? So the oxygen is needed. So that's why you need oxygen to give the meat red color. Okay. So otherwise, a lot of times if you go to buy meat, they put the meat under red light. Okay, for color consideration. But anyway, we know in general, oxygen is not desired. Okay, so that's why we want to use oxygen scavenging compounds. So as antioxidants, right? Antioxidant. For example, ascorbic acid and so on. For CO2, which is desired for use in food preservation and packaging, because CO2 can reduce microbial growth and decreases respiration rate of fresh cut fruits and vegetables, and can be used to overcome package collapse or partial vacuum caused by oxygen scavengers. But not always. One unique example is coffee. Okay, so the dissolved carbon dioxide formed after roasting of coffee might cause the package to burst. Okay, if the roast coffee is placed in a can or aluminum foil pouch. Okay. For insulin, we know which is a plant hormone, okay, which accelerates rapidly by increasing the respiration rate of climacteric fruits and vegetables. So leads to the decreased shelf life. So that's why in general we do not want insulin, so we use insulin scavengers. So to summarize, we do not want oxygen. Okay, we do not want insulin, but we prefer CO2, right, when it comes to food preservation. Polymers have been used to generate both active and intelligent packaging. Okay. So for active packaging, it is the packaging that interact with food and the environment. So including packaging able to reduce, inhibit microbial growth, delay oxidation, and moisture migration, as well as respiration rate of fresh cut fruit and vegetables. Okay, so here is an example of active packaging. So the packaging is produced using biopolymer PLA and PCL, okay, through melting extrusion process. And also the packaging comes with lemon extract, cymon, and lysosome. Okay. So for cymon, which is fungicide, okay, and also we know lysosome, okay, can also stop the microorganism activities. So we can see for this packaging, if we look at the definition, so it has the function right to reduce, inhibit microbial growth. Okay. Now let's look at intelligent packaging, which is also called smart packaging. So for this type of packaging that are capable of monitoring and communicating information about food quality using time, temperature, ripeness, leakage, physical shock, and so on. Okay. So for smart packaging, so the key information is okay, they have the capability to detect and communicate. Okay. The information, right, about the product. Okay. And also not only detect, communicate without direct action or measurement. Okay. So for example, for some packaging, okay, so they change color when temperature changes. Okay, so to indicate the quality of the product, for example, beverage, right? Especially for cold drinks. So you want to enjoy it when they are cool, right? So that's why you want to make sure you drink it at lower temperature. So they use the temperature changing material to indicate the coldness of the beverage. Biopolymer has also been used to reduce oil uptake during deep frying foods. So deep fat frying is the most common unit operation in food processing. Okay, for a long time. For example, potato chips, extruded snacks, fried chicken. Okay. So the reason why we care about deep fried foods because we know during the process the saturated fat, right, for these products is concerned. So we know there's a high correlation between saturated fat and obesity. So we know US is one of the most obese country in the world. So the obesity leads to all kinds of health issues, for example, heart diseases. Okay. So if we look at the mechanism contribute to the oil uptake, okay, during deep fried food. So there are two ways the oils, stay within the deep fried food. So first, iodine adheres to the surface after the product cools down. Second, the oils enter into the crust by suction through pores. Okay, when you remove the food from the fryer. Here is an example using biopolymers coating to reduce the oil uptake. So here they use hydrocolloid, okay, which made of two polysaccharides, gum and guar gum. So you can see their structure, okay. So guar gum, of course, from the guar plant. For gum, it's actually produced by fermentation, okay. So the interesting thing is they did modeling and extensive mathematical calculation, okay. So for the conclusion of the project, they notice this hydrocolloid coating, okay, actually reduce the heat transfer coefficients, which leads to the reduced oil uptake. Okay, so for food industry, okay, so it is one of the discipline, okay, the industry highly related to chemical engineering industry, okay. So I'm not sure whether I mentioned this now. My bachelor and master's degree both were in food science and engineering. Okay. So then, a long story. That was not really my choice of major. Okay, so different countries have different process. So they changed my major. So a lot of times there's confusion. So when we talk about food science engineering, people think about cooking, culinary science. Okay, so that's not the same thing. So here is a good example, right? You see we use science engineering to solve the food-related problems, right? It's not you just figure out how this coating works, but also we figure out the mechanism, okay? So which is related to thermodynamics and transport phenomena, okay? So this is a good example. And also for our program, currently we have elective called food engineering, which I teach. If you're interested in food industry, you can certainly consider taking the course. Also go back to what I mentioned, food engineering industry is highly related to the traditional chemical engineering industry. The reason is just think about the fact. So when it comes to food industry, okay, it's all down to how you massive produce the food product, right? We're not talking about the food you cook in kitchen in a small batch. We're talking about the massive production. So it's all pretty much down to chemical engineering. So you use similar processes to chemical engineering process. For example, for some snacks, they use the same type of machine, for example, extrusion machine. For you to produce plastic products, you actually use that to produce food, okay? So that's why for our students, if you know a little bit direct application, right, of chemical engineering in the food industry, so you will see a lot of the courses you are taking, right, actually you can apply. So second part I want to talk about biopolymers in food freezing and drying. So carbohydrate biopolymers has been used as drying aids in spray drying and freeze drying. So the problems are related to spray drying and freeze drying of food are stickiness, collapse, and color changes. So carbohydrates have been widely used to solve these problems during drying. Okay, so here are some major mechanism of functions shows how carbohydrates assist in drying process. For example, computation for moisture with host powder components. Okay, interpositioning of a physical barrier between particles, and increase the amorphous phase Tg glass transition temperature, and formation of a moisture protective barrier on the surface. Okay. If we look at biopolymers applications in food freezing, okay, mostly serve as cryoprotectants. Okay. If we take frozen dessert for example, we know frozen dessert is a broader term, right? So in general, for frozen desserts, we know ice cream, right? We also have custard, especially for Wisconsin. So custard is something I consider the best thing actually Wisconsin offer, and also gelatos, right? So we know for frozen dessert, the quality and shelf life is highly dependent on the ice crystal size. Okay. So in general, to get to the best quality, you want to form small ice crystals. Okay. So here is a picture from a very recent publication from AICHE magazine. Okay. So here shows a picture of the ice crystals. Okay. Of ice cream product. So in general, for ice cream, okay, and other frozen desserts, you want the crystal size to be lower than 50 micrometer. So the smaller crystal, okay, to which give you the smoother taste. Okay. So again, for frozen dessert, it depends on how you eat it, right? So for soft serve, we know there's now further freezing, right? So pretty much it is consumed during production. Okay, especially if you go to restaurants such as Caliber, right, cups, so you can see that how they produce custard on site. So for the custard that directly produce and serve you, those are soft serve. And if they further freeze them, right, to lower temperature, then there's more ice crystal formed for longer time storage, then those are not soft serve anymore. Okay. So for soft serve, we know in general tastes much better, right? If you go to grocery store buy the ones from the grocery store. So a lot of times, they can taste very different. It depends on how they are being stored. So what happened is during storage, recrystallization occurs. Okay, so recrystallization is the major problem. Okay, which leads to the quality decrease and also the storage life. Okay, so hydrocolloid can serve as stabilizers, okay, to control the ice recrystallization. So what is ice recrystallization? So we know, in general, let's say this is how the ice crystal looks, right? Okay, so let's say this is a product. They're very uniform, right, in size and also relatively small. Okay, so for water to freeze, in general, there has to be a process called nucleation. So called seeds. Okay. So once you have the small seeds, and then it starts to grow right into larger size of ice crystals. Okay. So if the temperature, let's say, increase during storage, what happened is some ice, they're going to melt, right? But if the temperature is high and low enough, so the melt ice, okay, that can refreeze. So during this process, you still have ice crystals. So then the ice crystals now serve as the seed. Okay, then you get much larger ice crystals. So the refreeze of melt ice is recrystallization. So recrystallization leads to large crystals formation. So this is why we do not want recrystallization to occur, because for the quality and the taste, we know we want a small, right, uniform size crystals, because the size of ice crystals determines the quality of frozen dessert. Okay, so again, during recrystallization, mostly the temperature is still low enough, right? So the melt ice, the water can refreeze. During this process, they use the remaining ice crystals as the seed, so they form much larger ice crystals. Okay. So the hydrocolloid stabilizing ice cream improve the smoothness, give uniformity of product, resistance to melting, improve the handling properties, and hinder crystal growth as temperature fluctuates during storage. So that's why when you choose ice cream or other frozen desserts in grocery store, always check the packaging. So if you see the large ice chunk, okay, from the outside the package, you don't want them. Okay, thankfully there was significant temperature fluctuation. Okay. And also, the hydrocolloids have a significant impact on frozen dough. Okay. So that can induce structure changes in the main components of wheat flour systems, and also that can increase water retention and loaf volumes, and decrease the firmness and the starch retrogradation, and also provide stability, help to minimize negative effects of freeze and frozen stage on starch-based products. Okay, so this is all for lectures 22 and 23. Okay, see you next time.